Good morning, everybody. How are you all? This is Dr. Nandi. I'm back again today. We are going to talk about mass and energy analysis of control volume part 2. So here I go. If we neglect the changes in kinetic and potential energies as fluid passes through an adiabatic turbine, having one entrance and one exit, the conservation of mass and steady state first flow becomes. So mass flow rate coming in is equal to mass flow rate going out. Energy, rate of energy coming in is rate of energy going out. Hence, for the last equation, energy coming in, rate of energy coming in can be written as Q dot net plus sigma, means sum of M1 dot is mass flow rate coming in parenthesis, the energy, internal energy, H enthalpy plus kinetic energy plus potential energy is equal to, that is coming in, going out is the net work produced by the system flow rate, again with respect to time, plus flow rate times coming out times the energy for each exit, and on the left you have for each inlet. Remember the term in sigma parenthesis, sigma means sum of energy coming in, and on the right hand side, sum of energy going out. So if you neglect Q dot net and W dot net because it's an adiabatic system, no heat exchange or work exchange with the outside, you can write, and you neglect the kinetic energy and potential energy, you write M1 dot H1 coming in is equal to M2 dot H2 plus W dot out, the workout. So what is W dot out? You solve for W dot out by subtracting M2 dot H2 dot H2 from both sides is equal to M1 dot H1 minus M2 dot H2, but the mass flow rate is constant, so net work coming out is equal to this m dot times change in enthalpy, basically change in enthalpy per unit mass multiplied by the mass flow rate. Example, high pressure air at 1300 Kelvin flows into an aircraft gas turbine and undergoes a steady state, steady flow adiabatic process to the turbine exit at 660 Kelvin. Calculate the work done per unit mass of air flowing through the turbine when the temperature dependent data are used. When part B, CP average at the average temperature is used and CP at 300 Kelvin is used. What is our control volume? Turbine. Property relation. Assume air is an ideal gas and use ideal gas relations. Process steady state, steady flow, adiabatic process. So again, we will use the equation from the last equation. Net work coming out is equal to mass flow rate times change in enthalpy from the entrance to the exit, okay, per unit mass. So W out, work output per unit mass, is net work out per unit time per divided by per mass flow rate. And we can use air tables, to calculate, to determine H1 and H2 from the tables, subtract them out, W out is equal to, again, the difference between small W out and big W out, small W out is per unit mass, okay? If you use CP average at 300 Kelvin of 1.138 kilojoule per kilogram Kelvin, then that is the answer for W out. What is that difference on the previous one? This is 728.3. Previous one was 725.5 kilojoule per kilogram. On the other hand, if you use the temperature CP at 300 K, you get a little bit less amount of work. So compressor and fans are essentially the same devices. However, compressors operate over a large pressure ratios, P2 over P1. Fans axial flow compressors are made of several fan blade-like stages, as shown on the previous slide. If we neglect the changes in kinetic and potential energies as the fluid draws to an adiabatic compressor having one entrance and one exit, the steady state, steady flow, first law or conservation of energy equation becomes again the same thing. W dot M is equal to M dot H2 minus H1. Nitrogen gas is compressed in a steady state, steady flow adiabatic process from zero point 0.1 megapascal at 25 degrees Celsius. During the compression process, the temperature becomes 125 degrees Celsius. If the mass flow rate is zero point 0.2 kilograms per second, determine the work done on the nitrogen in kilowatt. So control volume is the compressor property relation. Assume nitrogen is an ideal gas and use ideal gas relations. Process is adiabatic steady flow. Again, we are going to use W dot M is equal to M dot times H2 minus H1. So we calculate Wm dot, small Wm dot, which is the work output or work coming, sorry, W in is the work coming in. W dot in is the rate of work coming in plus divided by mass flow rate coming in. It gives you the specific work coming in is equal to H2 minus H in. Okay, okay. And here you go. So we calculate W dot in, from which we calculate capital W dot M, which is for the total mass, and it's 20.78 kilowatt. Okay. Another application. Consider fluid flowing through a one entrance, one exit porous plug. The fluid experiences a pressure drop as it flows through the plug. No net work is done by the fluid. Assume the process is adiabatic and the kinetic and potential energies are neglected, and the conservation of mass and energy equation becomes okay. Yeah, here one interesting point is the mass flow rate remains constant. Mass flow rate coming in is equal to mass flow rate going out at the exit. Okay, and therefore the internal energy HI at the entrance is equal to at the exit. Okay, coming in is equal to the exit, from which the exit is equal to EI. When throttling, temperature at the exit is equal to temperature coming in. When throttling an ideal gas, the temperature does not change. We will see later in chapter 11 that the throttling process is an important process in the refrigeration cycle. A throttling device may be used to determine the enthalpy of saturated steam. The steam is throttled from the pressure in the pipe to ambient pressure in the calorimeter. The pressure drop is sufficient to superheat the steam in the calorimeter. Thus, the temperature and the pressure in the calorimeter will specify the enthalpy of the steam in the pipe. Okay. One way to determine the quality of saturated steam is to throttle the steam to a low enough pressure that it exists as a superheated vapor. Saturated steam at zero point 0.4 megapascal is throttled to zero point 0.1 megapascal, 100 degrees Celsius. Determine the quality of the steam at zero point 0.4 megapascal. So control volume is the throttle, property relation steam tables. Okay, process is steady state, steady flow, no work, no heat exchange, neglect kinetic and potential energy, one entrance, one exit. Therefore, conservation principle first is conservation of mass. Mass coming in is equal to mass flow going out, mass rate, I should say, because of the dot, which is same saying that it's a constant mass flow rate process. And if you plug it in constant mass flow rate process, enthalpies at the coming in is equal to at the entrance is equal to entrance enthalpy at the exit H1 equal to H2. So we can find out the enthalpy at the exit from H1, and then we know how much is the quality at the exit by this formula. So this is the quality of the steam at the exit. Mixing chambers, mixing of two fluid occurs fluently in engineering applications. The section where the mixing takes place is called a mixing chamber. The ordinary shower is an example of mixing chamber. The T elbow section in the figure below, the mixing chamber and maybe a sample, okay? And maybe as simple as half-inch copper T. Okay, so you from one side you have hot water, and other side cold water, they mix and come out of the shower. Steam at zero point 0.2 megapascal, 300 degrees Celsius enters a mixing chamber and is mixed with cold water at 20 degrees Celsius, zero point 0.2 megapascal to produce 20 kilograms per second of saturated liquid water at zero point 0.2 megapascal. What are the required steam and cold water flow rate? So here is a picture in the control volume mixing chamber. Steam is coming in as well as cold water. Number one and cold water number two. They mix together, comes out as saturated water indicated by letter 3 or number 3. So control volume is the mixing chamber, property relation steam chamber, steam tables, process is assume steady flow, adiabatic mixing with no work. So M2 dot is M1 plus M2 coming M1 dot plus M2 dot time flow rate of mass for steam 1 plus time flow rate of water that is control cold water 2 is equal to M3 dot, from which we can calculate M2 dot is equal to M3 dot minus M1 dot, and then we do the energy balance. Okay, according to the sketch called mass control crosses the control surface, neglecting kinetic and potential energies and not noting the process is adiabatic with no work. We have two entrants and one exit. So again, what is the bottom line? Enthalpy coming in must be equal to the enthalpy going out, from which we can solve for M1 dot. Okay, and that is the mass flow rate of the steam coming in. And then we find out those H1, H2, H1 value from the temperature and pressure condition and so forth. We find out H2 also. So basically we need to find out H1, H2, H3 from the steam tables, plug it in, calculate M1 dot, and then M2 dot is equal to M3 dot going out minus M1 dot. Okay, so here you go. Heat exchangers are normally well-insulated devices that allow energy exchange between hot and cold fluids. The pumps, fans, and blowers causing fluids to flow across the control surface are normally located outside the control surface. So you have fluid B coming in in the top picture at 70 degrees Celsius flowing outside of the pipe. Inside the pipe is fluid A coming in at 20 Celsius. Of course, your goal is to have heat exchange from between fluid B and fluid A, so fluid A heats up. Okay. So they are showing different system. Okay. So let's see the fluid B coming in, and this is the control volume boundary is shown. Okay. And then fluid going out, B is shown. System is entire heat exchanger. So on the bottom left, you have the system as the entire heat exchanger. Q of the control volume equal to 0. Okay, no heat exchange with the outside. And in the bottom right corner, you have the system as the fluid A inside the pipe. And Q control volume equal to 0. Air is heated in a heat exchanger by hot water. The water enters the heat exchanger at 45 degrees Celsius and experiences a 20 degrees Celsius drop in temperature. As the air passes to the heat exchanger, its temperature is increased by 25 degrees Celsius. Determine the ratio of the mass flow rate of air to mass flow rate of water. Okay, control volume is the heat exchanger, air ideal gas law, relations, water, steam tables or incompressible liquid results, process, assume adiabatic and steady flow. So again, uh, the mass flow rate is constant. For two entrances, two exits, the conservation of mass becomes m dot in is equal to m dot out. Okay. So m dot air in plus m dot water in or position 1 is equal to m dot average m dot air out to position 2 plus m dot water 2. M dot is the mass flow rate. For two fluid streams that exchange energy but do not mix, it is better to conserve the mass for the fluid stream separately. So that means m dot air 1 is equal to m dot air 2 is equal to m dot air. No change in mass flow rate of air, no change in mass flow rate of water. And conservation of energy according to sketched control volume, mass crosses the control surface, but no work or heat crosses the control surface. Neglecting the kinetic and potential energy, we have for steady flow. So enthalpy of the air coming in plus enthalpy of the water coming in is equal to enthalpy of the air going out plus total enthalpy of the water going out. So total enthalpy is coming in is equal to total enthalpy coming out, from which you find the ratio of flow rate of air to flow rate of water. So you have to look up in the steam table. We assume that air has a constant specific heat at 300 Kelvin, table A, appendix 2A. We don't know the actual temperatures, just the temperature difference. Because we know the initial and final temperatures for the water, we can use either the incompressible fluid result or steam tables for its properties. Using incompressible fluid approach for water, Cp of water, that is it is incompressible, constant specific heat at constant pressure is 4.18 kilojoule per kilogram Kelvin. Plug it in, we know the drop in temperature. We do the same for air, and we get the mass of water. Um, so we want the ratio. So we have the water flow rate. Mass dot water is 3.33 kilogram average per second divided by kilogram water per second. Okay. Another problem, the flow of fluids through pipes and ducts is often a steady state, steady flow process. We normally neglect the kinetic and potential energy. However, conservation on the fluid situation, work and heat transfer may not be zero. So in a simple steam power plant, steam leaves the boiler at 3 megapascal, 600 degrees Celsius and enters a turbine at 2 megapascal, 500 degrees Celsius. Determine the inline heat transfer from the steam per kilogram mass flowing in the pipe from the boiler, between the boiler and the turbine. So control volume is the pipe section in which the heat flow loss occurs. Property relation steam tables, process is steady flow, conservation principle, mass coming in, mass rate coming in is mass rate going out. So from which we can say mass coming in equal to mass coming in is equal to a constant mass flow. And conservation of energy, change in energy, E in dot minus E out dot is equal to change in energy. But we know enthalpy coming in, so we can write delta E out going out, change in energy is M2 dot H2 plus Q out, from which we can calculate the flow rate of energy out or heat out, Q dot out, which is M dot times H1. And if you want to convert it to specific heat, change in heat flow rate, you divide it by the mass flow rate. And you calculate this way. Another example, here at 100 degrees Celsius, 0.15 megapascal, 40 meters per second flows through a converging duct with a mass flow rate of 0.2 kilograms per second. Air leaves the duct at 0.1 megapascal. So there's been drop in pressure and the speed is now 113.6 meters per second, increase in flow rate, increase in velocity. Okay. The exit to inlet duct area ratio is 0.5. Find the required rate of heat transfer to the air when no work is done by the air. Okay. So converging duct is the control volume property relation. Assume air is an ideal gas and use ideal gas relation. Process is steady flow. Again, m1 dot is equal to mt dot is equal to m from conservation of mass. And from conservation of energy, we can write m1 dot energy coming in plus heat coming in is equal to heat leaving the or energy leaving the system. Okay, from which we can calculate q dot in, which is the heat transfer. Okay, in the first law equation, the following are known: p1, t1, and h1 velocities, v dot v1, v2, and mass flow rate, and the ratios. The unknowns are q dot in and h2 or t2. Okay, so we find m1 dot is equal to m2 dot, and we solve for T2. T2 is T1 times the ratio of pressure, the ratio of areas, and the ratio of velocities. Okay, from which we can calculate Q dot in. Okay, liquid pumps. Okay. So the work required for pumping an incompressible liquid in an adiabatic steady flow process is given by this. Enthalpy difference is can be written as this change in internal energy but change in flow work, and you plug it in. So enthalpy difference reduces to difference in pressure specific volume products. Since V2 is equal to V1 equal to V, the work in the pumps become this. If we neglect change in kinetic and potential energy, then the pump work becomes m dot V, and two negatives make it positive. Okay. W dot is the net work done by the control volume, and it is noted that work is input to the pump. Input to the pump. So W dot input. So it is positive. Okay. If it had been output, then it would have been negative. Hence, two negatives make it positive. So W dot in pump is given by this m dot times specific volume flow rate, volume times P2 minus P1. M dot is the mass flow rate. So if we apply the above energy balance to a pipe section that has no pump, W dot is equal to 0, we obtain this equation from which we find the relationship between position pressure P2, the relationship between kinetic energy and potential energy, and the height at position 2 with that at position 1. Okay. The last equation is the famous Bernoulli's equation for frictionless. So pressure energy plus pressure energy. The first term is the pressure energy or flow work energy plus the kinetic energy plus the potential energy at position 2 is equal to the same at position 1. So this is the famous Bernoulli's equation for frictionless incompressible fluid through a pipe. Okay. Uniform state, uniform flow problems during unsteady energy transfer to or from an open system or controlled volumes. The system may have a change in stored energy and mass. Several unsteady thermodynamic problems may be treated as uniform state, uniform flow problems. The assumptions for uniform state, uniform flow are: the process takes place over a specified time period. The state of the mass within the control volume is uniform at any instant of time but may vary with time. The state of mass crossing the control volume is uniform and steady. The mass flow may be different at different control surface locations. To find the amount of mass crossing the control surface at a given location, we integrate the mass flow rate over the time period. Inlets m1 dot is equal to m1 dt over time period 0 to t. Exit is m dot exit times dt integration from 0 to t. So M2 minus M1 is integration from 0 to T, change in mass with respect to time over the control volume T. The uniform state, uniform flow conservation of mass becomes sigma mass in minus sigma mass exit is equal to M2 minus M1 crossing the control volume. The change in internal energy of the control volume during the flow period is M1, M2 U2 minus M1 U1 over the control volume is integration from 0 to T du by dt times dt. Or Q is equal to 0 to T Q dot dt and W is equal to W dot dt. Okay, the first law for uniform state uniform flow becomes Q minus W. The last equation is important. Enthalpy exiting minus enthalpy coming in plus M2 U2 minus M1 U1. Okay. What is U? U is the internal energy. So consider an evacuated, insulated, rigid tank connected to a closed valve through a high pressure line. The valve is opened and the tank is filled with fluid. If the fluid is an ideal gas, determine the final temperature in the tank when the tank pressure equals the line pressure. Okay. Control volume is the tank. Property relations, ideal gas relations. Assume uniform state, uniform flow. So conservation of mass leads us to one entrance, no exit, and initial mass is 0. This becomes mass internal is equal to M2 times control volume. Conservation of energy leads to a change in internal energy is equal to change in is equal to coming in flow work. Okay. And you plug it in. So change in internal energy is CV at constant volume T2. Specific heat at constant volume multiplied by change in temperature is equal to PIVI. Okay. If the fluid is air, K is equal to 1.4, and then they find the relations between CVT2 minus TI as KTI. Okay. Remember, K is incompressibility constant. K is equal to 1.4, and absolute temperature in the tank at the final state is 40% higher than the fluid absolute temperature in the supply line. The internal energy in the fuel tank differs from the internal energy of the supply line by the amount of flow work done to push the fluid from the line into the tank. That's it. I will stop here today. If you have any question, comment, write me a note. I'll definitely get back to you. Please give me a thumbs up if you like this video. I appreciate that. If you like this video, share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button. And please do not forget to watch me tomorrow when I'll be back with another interesting video. And thanks for watching. Take care. Have a nice day. And please subscribe to my channel by hitting the red subscribe button. Thanks. Take care. Have a nice day.